So now that we have a good understanding of what instantaneous rate of change is, we can transition to the next important concept of calculus called the derivative. So given a function f of x, the derivative is another function that will give us information about the instantaneous rate of change at a given x value for that original function f of x. We're going to look at three parts here. So the first part, we're going to talk about the limit definition of what a derivative actually is, very similar to instantaneous rate of change. We're then going to talk about when derivatives actually don't exist. And third, we're going to interpret graphs of these functions. All right? So let's start by defining this new thing that we call the derivative. All right, so before we do that, let's remember what instantaneous rate of change is. Instantaneous rate of change, as we know, is also the slope of the tangent line to the graph of f of x. So that's kind of our visual representation of what instantaneous rate of change is. Now, for this rate of change of some function f of x at x equals c, this is the definition, this limit definition here. The question that's going to lead into our definition of what a derivative is, what if we want to know these instantaneous rates of change at any point x? So not just at a fixed point c, but at any point x, okay? So you look at this definition up here, this limit definition, and we're going to replace that c with an x because we don't want to actually specify a c. We want it to be a general way for us to determine these slopes or these rates of change for any x. So if we replace that c, so see the c right up here, we replace that with an x, and we generate a new function. So a function is just a rule that depends on some variable, and in this case that's x. That function is going to tell us about the slope of the tangent line, i.e. the instantaneous rate of change, of the function at any point x, okay? And this new function is called the derivative. So I'm going to now pause this and formally define the derivative. So here's our limit definition of the derivative. And so if you're given a function y equals f of x, we say that the derivative of f of x, which is another function as we've stated, and the notation we use is given here. Now, just quickly on the notation, we say f prime. So there's just a little tally that indicates that it's the derivative, and the way that we say this is f prime. And it's defined to be, f prime of x is defined to be the limit as h goes to 0 of f of x plus h minus f of x over h. That's the same as the instantaneous rate of change where the c was replaced with an x, okay? This is a function. So this is a new function right now, and it represents the slope of the tangent line of the original function at some given value of x. All right, so that's really, really important, this interpretation of what this function actually does for us. Now, one of the tricky parts about the derivative is that there's four ways that we express this in terms of the notation that we use. The first way, so for this function y equals f of x, the first way you'll see the derivative is f prime of x, the one that we've talked about. Sometimes you'll see us write just y prime. It means the same thing. Also, we use this other definition with d's. And the d's, you can think of that as really signifying that we're taking a derivative, but it is notation that has historical significance. You have d of y, that's your function, over dx. And the x, this is your important, this is the independent variable. So what you see on the bottom is always the independent variable. And the fourth way that we express this is actually very similar to the third way. We say d dx, so that means derivative with respect to x of the function f of x. All right, so it's important to see these four different ways to express the same thing. The next step is to actually apply this limit definition to some examples. So I'm going to give you a bunch of functions, and we're going to use the definition and compute the limit to actually find the derivative. So for example, this part A here, this function f of x equals 2x plus 3, we're going to find the derivative with the limit definition. So right away, you need to write the first step, which is actually just using the definition. So you have limit as h goes to 0 of this. We actually call this the difference quotient. So if you ever hear that term, that's just this fraction here. Now the rest of it is a bunch of algebra, so you need to review those skills, and it can kind of get a little bit tedious. So I'm going to now dive into this example. As I mentioned last video, I really encourage you guys to use a little bit of a sidebar so we can do some work on the side before we take our limit. So in the sidebar, I want you to highlight the things that you're actually going to find in the sidebar, and that's particularly f of x plus h. So you want to find this, do your algebra off to the side so you don't make any mistakes before you bring it back. Okay, so f of x plus h, you're going to put x plus h in wherever you see the x in the original function. So we have 2 times x, which is now x plus h, plus 3. And simplify this as much as possible in the sidebar before you come back to your work. Okay, and that looks like the only thing that I actually need to find in my sidebar. So when I come back to my limit, I'm going to bring that blue piece, what I just got on the side here, and replace the f of x plus h. So that's 2x plus 2h plus 3. And this is a simple example, but as they get more complicated, if you follow this procedure, you'll benefit a lot. We're going to subtract the red part here, the f of x. I always recommend, obviously, putting parentheses, and f of x is just the function itself, 2x plus 3. Okay, those parentheses are super important because that minus sign is going to apply to the 2x and to the 3. So we do need to distribute this inside. The rest is just simplify this thing as much as you possibly can. All right, so we have 2x plus 2h plus 3 minus 2x minus 3, and you'll notice the 2x's and the 3's are going to cancel, which is really nice. So the next algebraic step, we have 2h left on top and an h left on the bottom. And all that's left now is to compute the limit. And I can't just input the h because I have a 0 in the denominator, but if you'll notice, the h's are going to cancel. So you're just left with the limit, as h goes to 0, of 2. Since there's no h on the inside of those parentheses, that limit is just equal to 2. So ultimately, what we find is that the derivative of this function is always equal to the quantity 2, to the constant 2. That's kind of an odd result, so let's discuss why that is. This function is actually a linear function, so it has a y-intercept of 3 and a slope of 2. It looks like this. The derivative, being 2, is telling me that no matter what point on the graph you're at, the slope of the tangent line will always be 2. And that's correct because these tangent lines, they all are just along that line, and they always have slope of 2. Okay, so that's the simplest example that you'll see. So we're going to slowly ramp up the difficulty. Let's now look at a quadratic function, 2x squared plus 1. We want to find the derivative, so we start with that limit definition of the derivative, just from the definition. And again, you start picking out the parts that you need to replace. So we're going to use the sidebar to find f of x plus h. This involves taking x plus h and putting it into the function. So you'll have wherever the x was, see what we're doing, wherever the x was, that's where you're now putting x plus h, okay? This is honestly the part that most people mess up, is the f of x plus h part, so be very, very careful with that. So now we're going to simplify this. I'm going to expand out the x plus h squared, so you get x squared plus h squared plus 2xh, all plus 1. The 2 distributes to each piece, so you end up with 2x squared plus 2h squared plus 4xh plus 1. Okay, now honestly, you do want to do this off to the side. I see so many times a lot of people they try to do all that work within the limit, and it gets really, really messy. So you come on back to that limit, and you're going to replace the blue part with what you have over there. So that's 2x squared plus 2h squared plus 4xh plus 1. And then you're subtracting the red part, which I'm going to circle right here. That's your red function, so that's just 2x squared plus 1. The parentheses are important because of that minus sign, so don't miss that. Okay. Then we just simplify that algebraically. Once you distribute in that negative sign, the 2x squareds are going to cancel, and the 1 will cancel, which is really nice. And all that you're left with is 2h squared plus 4xh over h. And all that's left between you and the derivative that we're trying to find is taking the limit. I can't just input the 0. I do need to simplify a little bit. So I'll factor out an h from the numerator. This is a common technique that'll help you simplify this. So all I'm doing is noticing that there's h terms in both pieces of the numerator. So you take that out, you factor that out, and that is going to cancel. Okay. So beautifully enough, all that we're left with is the limit as h goes to 0 of 2h plus 4x. All right. And now you can just input the 0 to where the h is. There's no holes, there's no asymptotes, there's nothing to worry about anymore. So you just will put 0 in for the h. The x is unaffected by the limit because the limit only deals with h. So the 2h will go away, and it'll leave you with an expression that represents the derivative, f prime of x, for this function f of x. And again, what is this derivative? This derivative is a function that tells us the slope of the tangent line to the graph of the function at any point x. Very, very important. To illustrate that further, you might be asked with a problem like this, once you find the derivative, you might be asked to then find the slope of the tangent line at a given point. So we might say, well, what is the slope of the tangent line to f of x at, say, x equals 5? Okay, well, we know that this derivative represents the slope of the tangent line at any point x. So to answer this question, all we need to do is take the derivative, evaluate it at 5, and I know that this is going to be my slope. All right, and that's how we can use the derivative to our advantage when dealing with tangent lines. So we're going to ramp up the difficulty one more level, and we'll look at a rational function. So this function here, 2 over x, of course we have to make sure x is non-zero, but this is our function we want to find the derivative. So again, limit definition, we're going to take this first piece, the f of x plus h, go off to the sidebar, make sure you do this correctly so that you have everything algebraically correct. The x plus h, that's going to replace the x from your function. There's nothing to simplify here, so we can bring that back to your limit. Now when you bring it back to the limit, we can put in all of our pieces, so that'll be 2 over x plus h on top, minus 2 over x for the f of x part, all divided by h. Okay. Difficulty here is working with fractions. So you have to look back at our algebra video from the start of the semester. In the numerator, you're going to want to combine those fractions. So remember how I taught you guys to do that. You take the numerator, multiply by that denominator, so you'll get 2x. Keep the sign the way it is, minus. Then this numerator times that denominator, so that'll be 2 times x plus h, divided by the two denominators multiplied together, which is x times x plus h. This is all still all over h, so things get a little bit messy here. Now as we simplify, a lot of stuff is gonna work out nicely for us. So this minus 2 gets distributed, the 2 and the negative sign, to the x and to the h. So in that top numerator, you'll have 2x minus 2x minus 2h, all over x times x plus h, and all of that is over h. Okay, I know this looks a little messy. We're going to talk about what it means in a second once I get it simplified. The two x's are going to cancel. Great. Now let's write what we have, and then I'm going to talk to you guys about a numerical example that'll help you see what we're looking at. So this is minus 2h all over x times x plus h, and that's over h. Okay. How do we simplify that? Well, let's recall kind of how we work with fractions. Suppose I asked you to take 1/3 and divide it by 5. So you have a fraction over a number. Well, that number on the bottom is really a fraction. It's really 5 over 1. And when you divide fractions, you'll actually multiply by the reciprocal of the denominator. So you end up with 1 over 15. So we're going to do the same thing here. And as you're dividing really by h over 1, so what you'll end up with is minus 2h over x times x plus h times 1 over h. Okay, that works out really nicely because those h's are going to cancel. And your final expression that you have within the limit is minus 2 over x times x plus h. And you're at the step now where you can actually input the 0 for the h, because there's no discontinuity that's going to happen, no zeros in the denominator that will happen when you do this. And you end up with an expression minus 2 over x squared. And that is precisely the derivative of the function that we started with. All right. This is one of the harder examples that you're going to see, but you have to try some of these on your own. Try to navigate through the algebra. That is the hardest part of this calculus problem. We're going to ramp up the difficulty one more time for a final example using this limit definition. Let's look at the square root of x. So this one is just a little bit tricky, but it actually is not too bad. So we're going to use the same limit definition. I don't need a sidebar this time because it's pretty straightforward what you're inputting. So f of x plus h is the square root of x plus h. F of x is just the square root of x, and that's all divided by h. So the question now becomes, how do we compute this limit? So that can be a little bit tricky because I can't just put the h in. So the technique here, and this is just for these types of problems with the square roots, is that we're going to actually multiply. So I'm going to get rid of this parenthesis for a second. I'm going to multiply the top and bottom of this expression by the same quantity. And we multiply by what we call the conjugate. The conjugate of this numerator here is the same expression, just with a plus. Okay, now since I'm multiplying top and bottom by the same amount, this is really just multiplying by 1, which is good. We're not changing anything about the quantity. So why does this work? How does it work? Let's see what happens. So in the numerator, you're going to end up with a product of the square root of x plus h minus the square root of x times the square root of x plus h plus the square root of x. And in the bottom, you'll have h times the square root of x plus h plus the square root of x. All right. Now, in the numerator, what you're going to need to do is actually expand this out. So you're going to have to distribute this out. So you start here, that'll go to that, and this guy will go here and to here as well. All right, I'm going to pause and do that for you. Once you do that distribution, you're going to get these 4 terms that you see here. So verify that you guys can get those. And then it's nice because those inside terms are actually going to cancel. The first 2 terms, when you multiply these 2 square roots, you just end up with x plus h. And when you multiply these 2 terms, you just end up with x. All right, and I actually do have an error right here, so this should be a minus right there in front of the 2 square roots. Okay, so the nice part is then, since I have x plus h and then I have minus an x, those x's are going to cancel. Okay, so all that you're left with inside of your limit, once all of this is done, is an h on top, an h on the bottom, and then the square root of x plus h plus the square root of x. Those h's are going to cancel, and then you can actually just finish by computing your limit and inputting the h. So you have x plus h plus the square root of x. And you can complete the example by inputting your h equal to 0, and you end up with just 1 over square root of x plus square root of x, which is 2 square root of x. And that's representative of your derivative for the function the square root of x. Okay? Now the key here, when you look back at our work, the key here was making sure that you do multiply by this special thing, which we call the conjugate. All right, and then also kind of navigating through the algebra. The second part of this lecture involves a discussion of when derivatives actually may not exist. Now, since your derivative, f prime, is defined by a limit, there are certainly cases where it may not exist, and there's actually 3 cases that we need to be aware of. The first case is a sharp corner. So if your graph of f of x has a sharp corner on it, for example, something that looks like this, then the derivative won't exist. And a good way to think about this is the derivative is the slope of the tangent line. So, for example, at this sharp corner, so let's say this is x equals a. At this sharp corner, if you wanted to find the tangent line, you wouldn't know how to draw the tangent line. You might draw it like this, someone else might draw it like that, a third person might come in and draw it like this. There's no tangent line that exists, okay? So sharp corner on the graph of f of x, then the derivative won't exist at that point, at only the sharp corner point. The second part is a discontinuity. So a function won't be differentiable if it's not continuous. So you might have a hole in your graph, you might have a break, like we saw before, and you might have maybe an asymptote. All right, so any sort of discontinuity, those are your three types: holes, jumps, and asymptotes. And the third time that a derivative does not technically exist is when you have a vertical tangent line, because then the derivative would be unbounded, it would be infinite. So for example, if you had a function that came in, went vertical, and then leveled off again, at the point where, in the middle here where it was vertical, so where technically your tangent line would be vertical, that derivative does not exist at that point, okay? So when we talk to you about when the derivative does not exist, you need to be aware that at a sharp corner it doesn't exist, at a discontinuity it doesn't exist, and any time that it appears to be vertical, it does not exist. Using what we just talked about regarding when derivatives don't exist, let's take this graph of some kind of crazy function, and let's determine all of the x values for which the derivative f prime doesn't exist. Okay, so we're going to list those bad f prime does not exist at these x values. So first of all, we'll move left to right. This is a bad point. That's a discontinuity, so that's definitely one of the points that the derivative does not exist. We then have a sharp point here, so this is also a bad point. So x equals 2. I have an asymptote. That's a point of discontinuity at x equals 4. There's a jump that appears to be at x equals 7. And so that's bad. That's a bad point right there. And it also appears that there's a location with a vertical tangent line. It might be a little bit hard to see by the way I drew this. And that occurs at x equals 9. So there actually are 5 points on this graph for which the derivative, the slope, a tangent line, does not exist. I want to pause here and just introduce one more vocab term that you should be familiar with. When a function f of x has a derivative, so meaning the derivative exists at all points, so there's no points where the derivative doesn't exist, we say that the function is differentiable. So you'll hear me use this term a lot. And a big topic that you can consider is what's the difference between differentiability, or being differentiable, and continuity. So let's explore that a little bit. So with continuity, we'll start there. I know a function is continuous provided that there are no holes, no breaks, and no asymptotes, okay? So as long as you don't have one of these situations, then you do have a continuous function. Differentiability, right? So these things are bad for continuity. For differentiability, the bad situations that you could see are the same if you have a hole, a break, or an asymptote. So at any time it's not continuous. But there's also a sharp corner and the special case of a vertical tangent line where you have something that goes vertical. Okay? So there's 5 situations where we don't have differentiability, and there's those 3 situations where we don't have continuity. So what we get from this is kind of a little theorem, we can actually call it. And the theorem says that if a function is differentiable, so if it's differentiable, then none of these bad situations occur, then it must be continuous. By that same token, it's important to know that not all continuous functions are differentiable. And the reason for that are these last 2 situations. Those situations are continuous, so I could draw a continuous function, say a nice roller coaster function that then has a sharp bend in it. Let's call that f of x. This function is continuous, but it is not differentiable because of that sharp point. All right, so it's important to understand the interplay between these two concepts. So let's complete this video lecture with just a quick discussion of how to actually interpret this new thing that we call the derivative. As I mentioned, and this is the most important part of the entire video, if you take nothing else from this video, make sure you take this big warning bubble here. F prime of x, okay, that's your derivative. This represents the slope of the tangent line of the function f of x at any point x. So for example, if I have a function f of x, and you tell me you pick any point x along the graph, say say you pick this value of x right here, and you drew a tangent line to that graph, say the tangent line is here, okay? That tangent line is going to have a slope, and that slope is going to be exactly equal to the derivative at that point x, okay? That's super important, very, very important for these applications. Make sure you know that bubble, put it on a note card, and throw it under your pillow. Okay, we're going to finish with example 3, and that's kind of interpreting a graph of f of x and what it means for f prime. If I give you a graph of f of x, and we ask just for intervals on which the derivative is positive, negative, and 0, all you're doing is essentially looking at the slopes of the tangent lines as you progress along this graph. So I always like the car analogy. Suppose you jump on a car and you're moving left to right. Whenever you're going uphill, those tangent lines are positive, or slopes are positive. That means your derivative is positive. If you're going downhill, your derivative is negative. Okay? If you peak out or hit a valley, then your derivative is 0. So in terms of the intervals for which it's positive, definitely from minus infinity. So if we're doing, let's do positives first. From minus infinity to minus 1, it will be positive, but not including minus 1 because it levels off. Then the car starts going down, and then it starts going back up again from 1 to infinity. So once the car gets back over here, it's going back uphill. Okay. So the way that we express this interval, we put a little u there, which means it's this first interval, minus infinity to minus 1, and the second interval as well. So that's when it's positive. Now if we talk about when it's negative, well, that's when it's going downhill. So you got your car and it's traveling downhill here, and so therefore that interval is going to be represented by minus 1 all the way to 1. Okay, that's when it'll be decreasing for x values from that interval. And finally, what are the points for which your derivative is equal to 0? Well, that's going to be your high points and your low points. So that'll occur at x equals minus 1 and x equals 1. We don't specifically have an interval, they're just discrete points. Okay? So practice this. Make sure you understand this big bubble here that I have in the warning sign, and work on using the limit definition of the derivative. In the next video, we're going to learn all sorts of shortcuts, so I'll see you then.